Hey everybody, this is Alex Merced and welcome to another video about optimizing data. In this video, what I want to do is talk about indexing, basically what is an index. And again, if you enjoy these videos, make sure to like, subscribe, leave a comment, and follow me on Twitter and LinkedIn. But what is an index? Now, an index is just a data structure that isn't your data. So it's not your actual like rows of data, okay? That makes it easier to find things in your data, okay? So for example, the example I like to think of is imagine that you have a kitchen, okay, and all the stuff is all over the place, okay. You kind of know where things are, but you still end up having to like look through all the drawers and the cabinets to find the thing that you want. But imagine you had a clipboard on the side that said, hey, the spoons are in this drawer. The plates are in this cabinet, okay. So in order for you to find your spoon a lot faster, you don't look where the spoons are. You don't look where in your kitchen. You look on the clipboard. It's a separate thing that makes finding the thing easier. Okay, that's all an index is. Okay, at the end of the day, an index is just going to be a separate data structure for making it easier to find things in your main data structure. So in terms of that, essentially, when you think about things like Apache Iceberg tables, the metadata is the index. Okay, it allows you to search through the list of files much quicker. And then within those Parquet files, the row group metadata essentially acts as an index, makes it easier to search through the file. Okay, but those are, oftentimes much more complex indexes. Let's just talk about sort of a simple index that you might find in a run-of-the-mill sort of relational database. Okay, so typically like your most basic of indexing basically is like the indexing you find in the back of a book, where you say, hey, the first time this word appears in the book is on this page. Okay, so in this case we have rows. So let's say I would create a index on genre, or let's say not genre, that's gonna take forever. Let's say on number of seasons. Okay, basically what I would do is maybe say, hey, we're gonna create an index on genre value, and we'll say here first row. So essentially we're creating this separate data set. And again, for those who are 2 steps ahead of me, don't worry, I'm going there. Okay, genre values, first row, and I might say, okay, so not genre values, the seasons value. Okay, and we'll say, okay, the first time the number 10 shows up, it's going to it shows up on row 2. Okay, and the first time we see 11, it's on row 3. First time we see 9, we see it on row 4. And because the data is not sorted, this index helps, but again, sorting can always enhance the benefit of others, because then basically, again, your data is more clustered. So those indexes will help you be able to skip many more rows than this is skipping. So because that's kind of the benefit here. You can skip all the rows before that point, and then only have to search from that point going forward in this sort of basic single column index. Okay, so 7. Okay, so the first time we see 7 is on row 5. First time we see, and you guys get the idea. So I'm going to just generate this index. I'll pause the video for a moment. Okay, so that's it. These are the actual values that are in that column. So then, for example, later on, I decided, hey, I want to go search for, I want to go, hey, give me all the records that have 15 seasons. Okay, then I can go to my index first and say, hey, you know what? I can start looking from row 8, which allows me to skip rows 2 through 7. Okay, so that saves me some time. Again, let's see what it would look like if I were to sort the data. So let me sort the data, because again, always the benefits of sorting your data along with these other optimization techniques. Well clustered data with, that's well partitioned and with smart indexes, you're going to get a lot of performance, because it's not about what you're doing here is you're not, with good optimization and good of these optimization features, you're not looking harder. You're not trying to push more processing power to look through it faster. You're looking through it smarter, which has 2 benefits. One, you don't need as much computing power, so the query is cheaper, okay, to do the same work, and it's faster. So faster and cheaper, that's a win. So data optimization goes a long way. But yeah, let me sort this data. So let's sort it by Filter, I'll do sort range, advanced, has a header row. Let's sort by number of seasons, and A to Z is fine. Okay, so now if I were to redo this index based on sort of the new sort order, it would look like so. Cool. So now here's my new index. So again, this is a separate data structure that allows me to look through here faster. So now if I want to find the records that have a seasons value of 15, okay, then I can just skip all the way to row 92. So look, all the records I get to skip, I can just kind of skip even evaluating those and go to 92 and then just evaluate the records here on out. So see, that speeds things up quite a bit. Now again, there's different ways you can structure this index. This is just like sort of like the simplest example. And even this, you typically is going to be done slightly differently because again, imagine that there's a lot of different season values, hundreds of numbers. Let's say there was a show that represented every number between 1 and 15. What still would have to happen is that when I say, hey, look for the show with 15 seasons, it would still have to traverse this list and say, look through each row to find the one that has seasons value of 15. And, again, imagine there's hundreds of values for that particular column. It might still take a while to go find the index entry to then go search the table. So a lot of times what happens is that this gets structured as a binary tree. Okay, so you might end up with something like this. Just kind of, let's see here, the median value is basically 9, let's say. So you say, okay, it would be like 9. That is on row 52. Then as the leafs, we would have 10, which is actually would be 7 on this side, 7, which is row 42. And then here we would have 10, which is on row 62. I'll just kind of finish typing this out. Okay, and then you'd have this tree structure. So essentially your median value would be the root of the tree. And then basically you would say, okay, hey, what is the first value above it, which is the 10, and the first value below it, 7, and that would give you sort of the 2 leaves of that tree, or of that node. Or actually, what's the median value below 9, and what's the median value below 10, and then you just kind of keep doing that, and you just keep kind of generating leaves as you go down. But now let's think about the traversal to find that index. So in this case, if I say, hey, I'm looking for all rows that have a number of 15, that have 15 seasons, I would start at the top of the tree and I say, okay, well, 15 is bigger than 9, so let's go down here. Well, 15 between 11 is bigger than 11, so technically what I should have done is this should have been 1172, and this should have been 1062. Because again, you want to use the median value. So then I get down to here and I go, well, 15 is bigger than 11, so then I'd go down here. So notice that's only 2 hops. Okay, so I got to that 15 much quicker than traversing every single row. So this is why a lot of times your index, and again, this probably should have been here, 612. Yeah, 612. And then this would be 742. Okay, just so that way we have a proper tree. Okay, and essentially you would just kind of, the more values you have, the larger that tree is, but that tree is going to be much faster. There's going to be a lot less steps to get to the specific spot you need in the tree. That's going to tell you which row to go look at than it would be in just a standard list like this. Okay, so there's 2 aspects to creating an effective index. Sort of, again, what are you referencing? And again, creating an index on a column that you actually, if I never search on number of seasons, then this is not helping me. Okay, because basically what's going to happen is that every time I update this table, this has to be updated. Okay, so there's a cost. Okay, so again, indexing has a cost because you have to update it every time you update the table. But again, it's the index itself, so having those references, but then also the structure of that index can also make it easier to use that index faster. Okay, and again, there's a variety of different types of indexes, and again, this isn't the only way you could do this. We could have captured like the range of rows that data exists in. Again, just trade-offs with every possibility as far as every different data structure, every different type of information you hold, because finding the first row of a particular value is a lot quicker than finding a range of rows, because then you have to kind of keep track of where it starts and ends and then do that for every value. So there are trade-offs. Now, in the story with like Apache Iceberg, because again, it acts as that index, and again, it tracks like the ranges of all sorts of values in its metadata, it benefits from the fact that Parquet has already done this, because Parquet, all that data is kind of stored in its row group footers. So its row group footers actually have a lot of like, hey, here are the different types of values that we have, the range of values that this particular row group contains, and then generally has another row that summarizes the whole file. So then Apache Iceberg, instead of having to recalculate all this information, can roll up the information. So for a particular manifest in Apache Iceberg, it can just take all the Parquet files that manifest tracks and roll up their aggregated statistics to that manifest level, and then take all the manifests of a particular snapshot and roll those stats up to the manifest list. Okay, allowing for, again, effective sort of pruning at the high level, and then you keep going more granular and keep narrowing things down. So there's different ways you can approach this. But that's what all-in index is. Again, different databases offer different varieties of index. But again, always think about sort of, is the index based on something that I specifically filter on? Again, if I never filter a number of seasons, just creating an index on it would speed up queries on number of seasons, but no one queries that. I'm now slowing down every time I update the table. Okay, trade-offs. That's everything in this data space. And, thinking about how to balance out your needs for writes and reads without hurting the other one too much. Okay, so I'll see you all in the next one.